Hello. Today, I will describe how Google's NAPA data warehouse system achieves robust performance for a wide spectrum of queries. I am Jun Tatemura, presenting on behalf of our team in Google. NAPA is Google's internal data warehouse system that has been operational for years, serving billions of queries per day with sub-second tail latency, while receiving high-throughput data ingestion as much as petabytes per day. NAP has been used not only for internal backend analysis, but also for external information serving. We have presented NAPA's overall architecture previously. Today, I will focus on one of its challenging problems, parallel query execution. Why parallel query execution can be so challenging in NAPA? That is what I will describe next. Our user has various analytic needs on the same dataset, requiring both low latency lookup queries and high throughput scan queries. NAPA serves such a wide spectrum of queries in one store, which is a challenging problem, as I will show. Alternatively, one might use multiple specialized copies for different types of queries. For example, key value stores for lookup and parallel relational databases for large scan. Such approach would be more expensive, complicated, and inflexible than the single store approach of NAPA. When we call lookup queries in NAPA, they are not simple lookup of individual key value pairs, but they are actually highly selective analytic queries, which we call many key lookup queries. A query selects and groups many points in multiple dimensions. From such dimensional selection, we identify prefix keys and use them to look up data by index. Here's an example. Suppose a table has 4 dimensions K1, K2, K3, K4, forming the compound primary key, and the query selects values for K1 and K2. Then we can form prefix key ranges K1, K2 from cross product of these values. Each prefix key range will match a varying number of consecutive rows in the sorted data. Then, how can we execute a many key lookup query in parallel in order to achieve sub-second latency? We might execute lookups of the individual prefix keys in parallel. This is a common idea in the key value store system to look up key value pairs. However, the problem is the skewed distribution in the data. Note that our key is a prefix key, and the size of matching data can be very different among prefix key instances. For example, if a dimension represents a customer ID, a small number of big customers may hold a large fraction of the data. In such a case, one prefix can be huge, while other prefix can be tiny, which we cannot tell only from the query text. To achieve sub-second latency, we need a parallel scan over a large number of rows matching with a huge prefix. Another approach is data partitioning, which is a common idea in parallel relational databases. We can split the content of the table by range or hash partitioning and store them separately. Then execute the query in partitions individually in parallel. The problem is that one partition size does not fit all in our case. For many key lookup, we need the partition size to be 100 megabytes or smaller. But that is too small to run a large scan efficiently. Later, we will show experiments to confirm this intuition. So we have adopted a different approach, query-specific partitioning. Instead of splitting the data offline, we split the scan range of query individually. NAPA takes a disaggregated storage model, letting query servers seamlessly access any part of the data. We split the query scan range based on the estimated cost and dispatch them to those query servers. Now the question is how we can estimate the scan cost and generate partitions evenly. First, what exactly is the scan cost in NAPA? To understand that, I will describe NAPA's data model. To serve efficient analytic queries under high-throughput ingestion, NAPA employed the well-known LSM tree, a log structured merge tree. The data is stored as multiple datasets called deltas. New ingestion will be added to the dataset as a new delta. As a result, updates on the same row can appear in multiple deltas that are ingested over time. The query execution needs to resolve these multiple occurrences in order to identify the current value. To perform many key lookup over an LSM tree, we need to merge lookup results from individual deltas to identify the current values. We materialize a B-tree index per delta, perform index scan concurrently, and merge them to output the values. We will consider this lookup merge cost to split the scan range evenly. Here is one challenge in the performance of query-specific partitioning. Note that the time to perform partitioning is included in the end-to-end latency of the query. So we need to consider a trade-off between accuracy and latency of partitioning. If it is very accurate but slow, the partitioning time itself can take the significant fraction of the query latency. On the other hand, if it is very fast but inaccurate, a skewed partitioning can take longer time to execute. In either case, the query can be too slow. So the challenge is to find good enough partition fast using the stats of the current dataset. Our approach is to leverage the B-trees of the deltas, which are already materialized for querying. If we embed sizes between boundary keys in every index node, we can regard a B-tree as equidepth histogram in various granularities at different levels of the tree. Gathering the stats from B-trees will give a good idea on the cost of lookup merge scan over the LSM tree. We exploit B-tree hierarchy as adaptive granularity of key samples to retrieve index nodes only as much as we need. We have developed a partitioning algorithm that retrieves index nodes of the deltas only as much as we need for good enough partitions. Here is a high-level overview of the algorithm called progressive partitioning. We first match the query prefix keys with the root node of each B-tree and acquires matching entries. We construct the stats with matching entries from multiple deltas and try to find keys to split input evenly. If the constructed delta is not detailed enough to find good enough partitions, we will retrieve child index nodes to get more detailed matching entries. Then we build refined stats and find split keys again. Repeat this until we find good enough for best possible partitions. Now, for details, how can we determine good enough partitions? That's what we cover next. The estimation of size and accuracy of the partition range is done as follows. From B-tree nodes, we get entries matching with query prefix keys. Each matching entry consists of a pair of index keys and the size in between. We merge matching entries from multiple deltas to create a sorted list of keys. We use this information to estimate the size of a partition between two split keys S1 and S2. The maximum estimate is given as the sum of entries overlapping with partition range. Minimum estimate is given from the entries contained by the partition range. With max and min sizes, we derive the average estimate size and the error ratio. If the error ratio is smaller than the given threshold, we call the partition size accurate enough. Otherwise, we need more fine-grained entries in a lower level, following the entries that overlap but are not contained by the partition range. Please see the paper for details of the search algorithm using this size estimation. Now, I will show experiment results to demonstrate the validity and effectiveness of our approach. To evaluate query-specific partitioning and the progressive algorithm, we use two types of baselines, respectively. First, fixed-size data partitioning. Second, query-specific but non-progressive partitioning. To demonstrate that our partitioning solves the real problem in NAPA, we use the real NAPA system and the real production dataset. We use benchmark queries to control parameters. We also use production query log to confirm that the observations in the benchmark are consistent with the actual workload. Please see the paper for the details. In the first experiment, the baseline uses predetermined partitions with a fixed size, emulating the data partitioning approach. Query-specific partitioning shows speed up when we increase the target number of partitions up to 100. But the predetermined partitioning does not show the same speed up, even when the size is as small as 250 megabytes. In the paper, we show that the performance of production query is consistent with these observations. The experiment confirms our earlier statement that many key lookup queries need the partition size in order of 100 megabytes or smaller. This means that one partition size does not fit all for our workloads having both lookup and large scan. In the second experiment, the baseline also uses query-specific partitioning based on B-trees. But the difference is that the baseline only uses one particular level of index tree, while the progressive partitioning selects the levels adaptively. The baseline emulates the case of fixed sampling. We control the selectivity of the benchmark query to make the prefix ranges larger or smaller. When we always use keys from level 0, which is the leaf level, they are too many for large queries. The partitioning is accurate, but takes longer time, resulting in performance regression compared to the progressive partitioning. On the other hand, if we always use keys from level 1, which is the parent of the leaf node, they are too few for small queries. The partitioning is fast, but its quality is worse, resulting in performance regression as well. This result depicts the trade-off between accuracy and the latency, as mentioned earlier. The progressive algorithm shows robust performance across a wide range of selectivity, addressing this trade-off by retrieving index nodes just as much as we need for accurate enough partitioning. In the paper, experiments show consistent observations in production queries. Note that the experiment measures the performance under the warm distributed cache. In production, the tail performance regression will be much worse due to more I/O cost. The adaptive approach in progressive algorithm helps for robust tail performance in the real system. In conclusion, one of NAPA's challenges was serving many key lookup queries and large scan queries in one store. Our solution is query-specific partitioning with the progressive algorithm. The experiments demonstrate the need and effectiveness of this solution. Progressive partitioning has been in operation for many years, serving billions of queries per day with robust performance. Our lesson is designing for tail performance is non-trivial and critical in NAPA scale in order to serve a wide spectrum of queries with highly skewed distribution in one store. Thank you for your attention.